So hi, my name is Yaron. I'm currently a software engineer at Microsoft, but I recently finished my my studies here. Became a Master of Science with the guidance of Tal Moran, and my thesis is on the subject of Bitcoin or cryptocurrencies in general. It's titled "Cheap Support for Complex Spending Conditions in a UTXO Ledger." A UTXO ledger it stands for Unspent Transaction Output Ledgers, and it refers to a type of transactions, a type of ledgers. And I'll be talking all about it, but first we'll start with some a brief description of some features in Bitcoin. So a naive way, or a more naive way of modeling a currency system is by using accounts. Each account has an associated identifier, or it is associated with someone, and it also has a balance. So this is the more intuitive way of modeling a currency system, but Bitcoin takes a different approach. The main abstraction in Bitcoin is the transaction. The transactions are added in blocks, and which make the blockchain. Each block points to its predecessor, and it consists of transactions. And here are two transactions. The one at the top has 2 inputs and 1 output, and the one at the bottom has 2 inputs and 3 outputs. And as you can see, each transaction is made up of inputs and outputs. Each output specifies the amount, an amount and the condition, and can be thought of as a coin, whose value is specified in the output, and it may only be spent if the condition it specifies is satisfied. Each input points to an output, which it spends. We say that this input spends the output it references, and it provides some data. In terms of spending and validity, validity is checked by miners when considering whether a transaction may be added to the blockchain. What they do essentially for each transaction is check that all inputs are valid, and we'll dive into that immediately. And they also see that there is no, the amount of outgoing coins, the amount that the outputs specify, is larger than the incoming coins. And this is something they check so that no new money is minted. An input may spend an output if the output is unspent. This is to prevent double spending. And they also verify that the condition in the output is satisfied by the data provided by the input. So, in other words, an output may only be spent once, and you may only spend an output if you can provide data satisfying the condition. So this is key. A miner. Okay, so the unspent outputs represent all the available funds in the system, available for spending of all the players in the system. And so the miners, which verify transactions, only need to remember which transaction outputs are still unspent. And this is key because they only need to, this type of ledgers is named for the quality of being able to capture all the state inside a single state, inside a single set of unspent outputs. And so the main use of cryptocurrencies is the transfer of coins, obviously. In terms of outputs and inputs, this will require signature verification, in the sense that the input of a transaction spending an output would contain the signature of the receiver of the funds, proving that he is the owner of the transaction, of the spending transaction. And the output condition would verify that this signature is indeed valid. Many of the more interesting uses require more. In general, a transfer of X coins from party S to party R, from a sender to a receiver, should occur only if conditions A and B hold. And so Bitcoin and other related cryptocurrencies based on Bitcoin place strict limits on the language used to phrase contracts or conditions. Chiefly, there are no loops, which renders the language not Turing complete. Not only that, but the conditions are of constant. They are limited. Their length is limited, and so this makes higher level protocols harder to implement. Relaxing these limits requires comes at a cost and requires some increased complexity. For example, Ethereum handles this by implementing a Turing complete language, which allows them to express conditions that are stateful and that are Turing complete. But this any relaxation it comes with a cost of itself. It makes the accounting of the currency harder to implement. So while Bitcoin is less expressive than Ethereum, it is easier to prove right, and also more performant, and it is still dominates the market. So our contributions are first to take Bitcoin as a less expressive ledger and make a slight modification to it. We show how to augment it, the Bitcoin language, with a single innocuous opcode, arriving at a variant we refer to as Bitcoin Plus. And this can help us create richer meta output conditions. Particularly, as an example of what we did is implement arbitrarily sized Boolean circuit conditions, which means that, and the thing to note here is that you cannot implement Boolean circuit conditions of arbitrary size in Bitcoin. So this is what we are aiming at. This is our goal. And after defining this opcode, and we show how to compile how we compile an arbitrarily sized Boolean circuit condition into smaller transactions that are supported by the underlying ledger. We define an idea, and we also want to prove that this is that our protocol is secure. So we defined an ideal ledger and a generic protocol that realizes a meta ledger over a base ledger. A base ledger is is a ledger whose output conditions are in the some base language, and a meta ledger is an overlay in which the conditions are phrased in a higher level language. For example, in our case, arbitrarily sized Boolean circuit conditions. And so we want to prove this, we prove that this protocol is secure in the universal composability framework. And this is our setting, and this is what we focus on now. We have a transaction, and this transaction has one input and one output. The input is simple, but the output contains a condition. The condition is A and not B or C. And this is a circuit, a toy example, but still a circuit. And we can, by using this example, we can show the construction and see how this is done for any size of a circuit. And our goal, given this setting, is to compile it to an equivalent set of base transactions with conditions that are valid in the underlying ledger. And we refer to this equivalent set of base transactions as fragments. Each fragment has a very small output condition, and the fragments are funded by the same input that we had in the original transaction. There also exists a single output that corresponds to the output of the original transaction, in that they both hold the same reward amount. And also, and this is our soundness requirement, if you can spend that output, then you can extract an assignment satisfying the circuit in the condition of the original circuit. Let's see how we do this. This is our original transaction, and it holds the rewards. And we first create input bit transactions, meaning a transaction per each bit, TXA, TXB, and TXC. Each has two outputs, a positive and a negative output, and corresponding to the positive and negative Boolean values. And we introduce the concept of a label. We say that the label of a transaction is true if only the positive output was spent. Similarly, if we say that the label is false if only the negative output was spent. And this way we can express the conditions in the following transactions. So we now create a transaction for each gate. The first one, X, corresponds to the value in the wire of A and not B. It too has a positive and a negative output. And you can see that the positive output of this transaction may only be spent if the label of A is true and the label of B is false. So this is the condition, this is how we phrase it. Similarly, the negative output may only be spent if the label of A is false or the label of B is true. Next, we create a transaction for Y, which corresponds to the wire, the value on the wire of X or C. And the positive condition may be spent if the label of X is true or the label of C is true. And this is the output that holds the reward. As we said before, the one output corresponds to the original output. Now, as you can see, our original transaction had only one input, but now we have 5. So what we do is create another transaction. We call it the splitter transaction. And it has an output per component, per input bit or gate, and it splits the funds between them. It also has the input, the same input as did the original transaction. So this is our construction. This is what we do. But the thing to note here is that the input can be that corresponds to the input from the original transaction is the one found in the splitter. It's the same transaction, while the output corresponds to one of the outputs of the gate fragments. So we can also decompile it. If we see only the fragments, we can decompile them back to see to get the original transaction. We can understand the structure of the circuit from these transactions by looking at the outputs. And so we saw how to compile a circuit. Now we'll see how to compile an assignment. We have a similar one thing I would like to note. Sorry, before this. While this output, the original output, cannot be expressed in Bitcoin or Bitcoin Plus, our variant, the outputs or the condition in the outputs of the fragments can be expressed in Bitcoin Plus. This is the one key thing to note. So now we compile an assignment, or put differently, this is how we provide an assignment to the circuit. So we have a transaction which assigns the values true, false, and false to A, B, and C. And it references the output of the circuit transaction. The way we compile it is by creating input labeling transactions first. First, we create a transaction that labels the transaction A as positive. It spends the positive output of the transaction A. Next, we have a transaction that spends the negative output of transaction B, labeling it as false. And finally, we have another transaction for C that spends the negative output, labeling it as false. So now we can create gate labeling transactions. The first labels X. The way it does this is by spending the positive output. And this is possible because now, at this point in time when we attempt to spend the positive output, the label of A is already true, and the label of B is false. Next, we create a transaction that labels transaction Y. It spends the positive output, thereby claiming the reward. And the condition is satisfied because the label of X is now true at this point in time, and that's it. That's why you can claim it. So from these, the two things to note here. From the input bit labeling transactions, we can learn what's the assignment for the circuit that satisfies the circuit. This is the first thing. This is how we extract the assignment from the transactions, from the fragments. The second, and this is essentially how a decompiler would take the transactions on the right-hand side and output the assignment transaction. Okay, so we now see label is still it is still unclear how to implement label, and it is dependent on the underlying ledger. In our case, we took Bitcoin as a study case, and what we did to allow us to implement label is to introduce a new opcode. It is called op is TXO unspent, and it may be used in a condition, and it accepts an identifier of a transaction output, and it returns whether this output is unspent. And you may ask yourself, why didn't we use the more you would think it is easier to implement isTXO spent as opposed to unspent, but given that the miners need to maintain the UTXO, the unspent transaction output ledger at all times, this opcode is very easy to implement, and it only took 20 lines of code with comments and all. So given this opcode, we'd like to implement label. Consider this transaction X, it has two outputs. And consider the UTXO ledger after this transaction has been accepted to the ledger. There are 4 states with regard to these outputs. Either they're both in it, either they're both not in it, or only one of them is inside. Okay, so in which case, in the 2 cases on the right-hand side, we can definitely say that the label is defined and it is true and false. So we can replace or substitute label X is true with not is TXO unspent and is TXO unspent, that the positive output is not unspent and the negative output is unspent. And so this allows us to test for the true label. So our soundness, what we proved is that if the positive output of the last gate was spent, then we can extract the satisfying assignment. This is important. The reason why we chose this soundness is because higher level protocols require that the satisfying value is available. For example, the preimage of a hash. And we've proven this by induction on the depths of the component. And many higher level protocols that use the ledger require, yes, okay. So the protocol uses, it is decoupled from the compiler and the decompiler, and it realizes the meta ledger over the base ledger. We've proven that the protocol is secure in the universal composability framework, while the ideal functionality shouldn't need to compile or decompile, and the protocol should be secure for any compiler, decompiler satisfying some basic requirements. The ideal functionality, it conforms to what we expect of an ideal functionality in the sense that honest parties may send transactions, and that the adversary may choose the content of a block, and it is secure in all the senses we've said. There's consensus and liveness in the sense that the transaction of an honest party is sure to be published, and it is simpler to use in higher level protocols, and it is flexible in the sense that it allows to capture the meta ledger. Yes, so in summary, we extended Bitcoin to create Bitcoin Plus by introducing an opcode that allows us to query the state of an output, whether it is or isn't in the UTXO database. And we showed we shown in a compiler that compiles an arbitrary Boolean circuit into multiple fragments, and we showed an ideal ledger functionality and a generic protocol that realizes it. And what we hope to see is other languages being examined and have compilers written from them. For example, arbitrary long scripts as opposed to circuits. And we hope for, yeah. So that's about it. Thank you.